Okay, great. Thanks for the introduction. So indeed, I will talk about one collaboration within Software Center that we have been working on recently. And as Jan introduced, it is about propagating modifications from generated code back to the design model from which that code was originally generated. And so this is kind of the origin of the title there. But what about back again? So the there part is about we have managed, or we are working in a setting where already code is being generated from the design model, but now we want to propagate back modifications to the generated code back again to the model. So in the talk, I will try to generalize the problem a bit, explain a bit at a high level this project and the work we have been doing in that. So let me start by explaining the title a bit more. So the there part refers to code generation from a model. So let's say we have some model that is some abstract representation of code. Let's say we can, in terms of an analogy, since it's a lunch seminar, I thought it would be funny to create a lunch analogy. So let's say we have some kind of configuration for a lunch recipe where you say what kind of things you want to eat. And then from that, we have an automatic generation of a recipe from that. So we have the model on the left side, and from that we generate a code on the right side. And in the analogy, the code is a recipe, so it contains, let's say, the steps that you need to go through to create the food. Right? It's a kind of algorithm in the sense, in that sense. So far so good. We are there. We went from model to generated code, and this is in place in the setting where we are doing this project. Now, sometimes after generating this code or generating this recipe, we want to modify it. For example, depending on our specifics of our kitchen, right, or our diet, or just personal taste. In other words, where is the code deployed? Where is it executed? In what context does it need to run? You might need to change the code a bit, or in this case, you might make some modifications to the recipe to adjust to the specifics of the environment in which you want to use it. So, for example, we need to change the oven temperature of our in our recipe. We need to exchange some ingredient based on some allergy, for example, or we want to add some instructions to make it more to our personal taste. So now we end up with a kind of modified lunch recipe that we have personally modified, and the consequence of that is that now this modified lunch recipe and the model that we had originally, they are no longer consistent with each other. Right now we have introduced some inconsistency between the model and the code, and of course now at some later time, when we want to maintain this software, the model and the code, and we open this model, we would like that to be consistent with the code so that we can perform maintenance actions that make sense, because the model actually describes what is running in that code. But because of the modifications, this is no longer true. So what we want to do is we want to bring those modifications back to the model, and that's the part of the title that is back again, right? We need to complete this round trip from model to code, and then from code back to the model. So what we want to do is reflect the changes that we made manually in this code, so the changes to the lunch recipe, and we want to reflect those changes back into the model. So then we are there and back again. So this is typical kind of called round trip engineering, where we are going from model to code and from code back to model. And I would say there's not really it's very, very hard to kind of imagine a general solution to this, but we can look at one instance, and that's what we are doing in this project. So we will look into one instance and see how we completed the round trip in that instance. So I will continue now with a bit more detail into that. So how can we reflect the changes to the code into the model? Well, roughly we can have two options among other things. What we can do is we can reverse engineer a model from the code. So let's say we just take that entire code or that entire lunch recipe, and we instantiate from it a model that would describe it. Another option is that we propagate back only the delta, so only those modifications that we made, only the difference. Those are only propagated back to the model. So this is a more incremental approach where we look only at the difference. And typically in this kind of scenario, this incremental approach is preferred, because you can imagine that if you want to do this a lot of times, or if this code or model base is very large, then doing the reverse engineering might be quite costly to perform. So we are now choosing to propagate only the delta, so only the difference from that we made manually to this code. We want to propagate that back to the model. So then first problem is that we need to find out what exactly is the delta. What did we change? Imagine that the changes that we made to the recipe are just kind of scribbled notes on a kind of printouts, let's say, of the recipe. In the analogy, the changes are made directly on the target devices. So on the PLCs, there the code is changed, right? So this is a very different environment than the model originally. And so first, to be able to propagate back the changes that we made manually, we need to know what exactly we did. What exactly are the changes that we made manually compared to the model? But we cannot directly compare this lunch recipe on the right side with the model on the left side, right? They are kind of completely different syntax. This is kind of misaligned. So we need to figure out a way to be able to be able to detect or decide what changes were made manually to the code. So when we look a bit more closely at the setting in which we work, so we had on the one side the model, then code is generated and deployed on the PLC, and this is the kind of recipe that I was talking about, and in our setting it's persisted as XML. So this is deployed on the PLC, and then on that PLC there is of course this recipe running, and there it is also modified. So this star I used to indicate that this is a modified version of the generated code. So how can we now find the delta between, or the difference between the modified code and the model? So instead of comparing the modified code directly to the model, we will compare this modified code to the generated code, since this generated code and the model, they are consistent kind of by construction, right? Because the code is directly generated from the model, so there's no there are no changes there. So that part is completely consistent with the model. So if we can compare the generated code with the code that is now running on this PLC, then we can find out what are the differences, and then we can propagate those back to the model. So this sounds kind of okay, but of course there is a complication now. So there's a kind of complications in comparing these two artifacts, because during the deployment of the code onto the PLC, actually some extra things are added. So one thing that is added are libraries that are kind of contain common functionality, and they are loaded onto the PLC together when the generated code is deployed. So you can think about, let's say, common definitions in the analogy of recipes. Let's say there's, in the beginning of the cookbook, you have these parts that explain how to make basic dough, or how to make some creams that you need in multiple of the recipes. So let's say these common definitions are imported from libraries during deployment. And so what we get then is actually exported code, and now I put 2 stars to indicate it's kind of not only modified, but also has these libraries onto it. And the thing is that when we compare now this exported code with the generated code that we had originally, then it's you get a lot of changes that we are actually not interested in, because those changes that are coming from the libraries, we do not want to propagate those back to the model. We only want to find out those changes that we did manually. And to make matters worse, also during this PLC export, there are additional elements and additional things added to the exported code that we also don't want to see when we are propagating it back. So there can be, for example, extra elements that we don't know in the model. Let's say I wrote some comments or my own rating of the recipe. Right, this is not interesting in the model because we don't need that information to generate the code from that. Additionally, there are some changed elements in this during this export. So, for example, this is just kind of things that are done during the export. Let's say it writes integers as 3.0 instead of 3, as an example. So there's a lot of these kind of changes that, even though they are different when you literally would compare those two, they're actually not interesting at all for the propagation back to the model because they are not those changes that we made manually. So the key thing is that indeed we get a lot of this exported code is now actually quite a lot different than the generated code, but we want only a very small part of those differences. So what we want to do is kind of bridge the gap between this generated code on the one side and the exported code on the other side. So then the next question is, of course, how will we do that? So the idea is that in the first step, what we can see is that we can try to ignore new types of elements that are introduced in the recipe. They can be ignored. If I, for example, have on the left side in the generated code only ingredients, preparation steps, then some cooking steps, and then some serving steps to follow. Let's say on the right side in the exported and modified and so on code, I have also added a shopping list, and I wrote down my own experiences while cooking this, and I gave some star rating to the recipe. Then these elements are not needed in the model because I don't have them in the generated code. So if I don't have something in a type of element in the generated code, then I also don't need it in the model, right? So these things they are not of interest for the back propagation. So we can leave those out and try then to make the formats of the exported code and generated code the same. Because when the formats are the same, then we can compare them, and then the differences that we will detect then are the differences that actually we made manually. They are interesting. So what we want to do is to make, in terms of the code, we want to make the exported code conform to the schema of the generated code. So this is more in XML terms what we want to accomplish. So the way we are approaching this is by using higher order transformations, and so I will explain this in a few steps. So remember that the generated code is actually persisted in XML, so it is an XML file, and so our proposal is then to derive the schema from that XML file, and so this we also implemented, right? So we get the schema from this XML file, and then we insert this into a higher order transformation. And so a higher order transformation is just a transformation that outputs itself a transformation. And then, so to clarify, a transformation in this case is just, let's say, a function that I apply on an XML file, and I get out some other XML file. So this higher order transformation, we implemented this in XSLT. It's not so important, but the point is that we get out from this a transformation that we apply on the exported code. So this exported code that is modified and has these libraries and everything is in kind of used as input for this transformation, and what we get out is the recipe, but removed all those extra new elements that new types of elements that we didn't know about in the generated code. So if we had some new elements like the shopping list in the exported code, but we didn't know about this in the generated code, then now it is gone. So this is already one step closer to being able to compare. But notice now that when we would compare now the artifact that we have on the bottom right, still we have those extra information from the libraries. These basic recipe steps, let's say, that we still would see as different if we would compare the generated code with that. So still we want to get rid of those as well. So for that we just apply the same trick again actually. So what we will do is have an export of the libraries, and then create a different higher order transformation that basically it takes this exported code with now only the additional library information in it, and it will result in the recipe. So the transformation, what it does is it just keeps only those elements that are not library elements. And then what we end up with is modified code, so kind of modified recipe on the bottom right that is in the same format as the generated code was in the beginning. So now we are kind of almost happy. So we have those the generated code on the one side and the pruned exported code on the other side. So they are now in the final in the same format. So when we compare them, we expect to get only the kind of relevant changes, because the changes that are shown up now are only those that we made manually and not from that are just artifacts from coming from exportation or from the libraries or so on. But we need to be a bit clever about this comparison now. Since both of these are XML files, there might be occurring some changes that are actually not relevant. For example, the child order inside nodes. Let's say if you have a list of ingredients and you need milk and apples, or you need apples and milk, it's exactly the same, right? But if you naively compare two text files, you would see that as a difference. Also, this hides a bit of a danger, because you might imagine that in the steps of the recipe, there, of course, the order very much does make a difference, or that is important to notice. So this needs to be kind of handled with care, but you can solve that quite easily by just numbering the steps, and then it will show up as a difference anyway. So in short, what we need here is to make this comparison XML-aware, in the sense that it should ignore child order, it should ignore comments and so on. So it should ignore things that are also not relevant to the manual changes that we did, so not relevant for the back propagation. So we can do this, and then we get some output showing the differences. And we have created this output in two forms. So one is a kind of more human readable one, and the other one is a more machine readable one that we will use for the actual back propagation in the next step. So what we have is this delta with our manual changes. And what we are now, what is the next step, is to actually make those changes in the model, right? So to actually complete this round trip to go back again from the code to the model, making those changes. So currently, what we are working on is that exactly automating that exact step. So the first step was trying to identify the manual changes that were done. So that we managed to do using this pruning mechanism. And now we are working on automating this, making the changes into the model. So currently, this part is still manually done. But yeah, so it takes a bit of engineering effort also of course, in the modeling tool to allow for this back propagation. But it is quite possible when we have a list of all the elements that actually have changed. So in summary, we wanted to propagate the manual changes from the code back to the model. And to find out those changes, we compared the two code files, the generated code, which is consistent with the model kind of by construction, and then on the other side, the generated and deployed and modified code, to figure out exactly what are only the manual modifications that were done on site. And to be able to compare these, a lot need to be pruned from this generated and deployed and modified code files. And that approach I sketched before using these higher order transformations to get rid of stuff in a bit of a generic way. So the key of using those higher order transformations is that even when the schema changes of this generated code, then we do not need to change our approach will still work exactly the same, because we don't need to manually update our transformations, but instead the higher order transformation will generate a new transformation that will prune the deployed code appropriately. So this is the kind of sketch of the complete round trip to go there. So generating the code, this was already in place, generating code from the model, and now we can go also back again. So from the code back to the model. So it is important to note that we looked at kind of one instance of this problem, right? So our solution is heavily impacted by the specifics of this setting and by some technological constraints and so on, and by the fact that this code, for example, is in XML. So this gives some ideas to solve it. So in general, I think that the key is that, of course, when you start a project like this, there is never kind of a clean canvas. So, of course, it is not about sketching the perfect solution in a theoretical setting, but it is about migrating from what is currently there to something that is a bit more automated or a bit more supports a bit more this back propagation. And I want to just very briefly to finish comment on a bit, kind of zoom out a little bit and say that essentially what we are looking at is discussing a challenge of restoring consistency. And in this case, it is between this model and the generated code. But variations of this problem occur in many other settings, like consistency among model variants or among a system model and a code, where you have a bit of an abstraction gap there, or consistency between software design models and other models that are describing the same system, but from different viewpoints. And so what is the next step in our software center project, or as one step of many? We are doing a survey on this consistency management. So if you're using a model-based development or this kind of models in your in the development of your software systems, we would like you to ask you to fill that out. So I will send this out soon to all the software center companies as well. And yeah, so it will just ask you to fill that out. It should not take too long. It's about 12 questions, and they are mostly closed kind of multiple choice questions, so they should not take too long to answer. And we will, of course, anonymize your answers and try to write some research publication of our synthesis of all the answers. So this concludes my brief overview of the research we are working on. So the key takeaways are that we started from a setting where the code is generated from the model, but we didn't have any way back yet for the code changes. But of course, for maintainability and for managing different variants of this model and the code, they must be consistent with each other. And to manage that, we did some pruning of the files before being able to compare them using these higher order transformation setup that I briefly sketched. And at the last point, I will send out soon a questionnaire about consistency management, and it would greatly help our software center project if you could take 10 minutes to fill that out. So thank you very much, and we can do some questions now.